Have you ever thought about the nature of time? Is it absolute or can it change depending on how fast you're moving? As it happens, the answer to these questions is far from simple. It's a journey that takes us into the realm of physics and the mind-boggling world of relativity. You see, our everyday understanding of time is that it ticks away at the same speed no matter what we're doing or where we are. Yet, this isn't quite the case. According to the revolutionary ideas put forth by a certain Albert Einstein, time is not as rigid as we might think. It can stretch and squeeze, warp and weft. It's a dimension that's influenced by both speed and gravity. Well, it turns out that according to Einstein's theory of relativity, time can indeed slow down or speed up, depending on how fast you're moving. Let's dive into this mind-bending concept. In the early 20th century, Einstein shook the world of physics with his theory of relativity. This groundbreaking theory challenged our conventional understanding of space, time, and motion. To understand relativity, we need to grasp two fundamental ideas. The first is the concept of relative motion. Imagine you're sitting in a moving train and you toss a ball straight up. To you, the ball appears to go straight up and down. But to someone standing on a platform as the train whizzes by, the ball seems to follow a curved path. Both observations are correct depending on the observer's frame of reference. This is relative motion in a nutshell. The second idea is the constancy of the speed of light. No matter how fast you're moving, you'll always measure the speed of light to be about 300,000 kilometers per second. This is a radical idea, and it's not what we experience in our everyday lives. If you're driving at 100 kilometers per hour and you throw a ball forward at 10 kilometers per hour, someone standing by the roadside would see the ball moving at 110 kilometers per hour. But light doesn't play by these rules. If you're moving at half the speed of light and shine a flashlight forward, both you and a bystander would still measure the speed of the light beam as 300,000 kilometers per second. These two ideas, relative motion and the constancy of the speed of light, form the basis of Einstein's special theory of relativity. They allow us to make sense of the strange and counterintuitive phenomena that occur when objects move at speeds close to the speed of light. So, if the speed of light is constant for all observers, what does this mean for our perception of time? This question leads us to the fascinating concept of time dilation, which we'll explore in our next segment. Stay tuned. When we talk about time dilation, we're referring to the idea that time can stretch or shrink depending on your speed. Now, let's explore this concept a bit further. Imagine you're on a spaceship traveling close to the speed of light. You decide to measure how long it takes for a beam of light to travel from the floor to the ceiling of your spaceship. From your perspective inside the spaceship, the light beam travels in a straight line, and you might calculate that it takes, say, 1 microsecond. But here's where things get interesting. To an observer standing still on Earth, the spaceship is moving incredibly fast. From their perspective, the light beam inside the spaceship is not traveling in a straight line, but rather a diagonal one. Because of this, they would calculate the light beam's journey as taking longer than 1 microsecond. This is the essence of time dilation. Your spaceship and the Earth observer are both correct in their measurements, but they observe different amounts of time for the same event. This is because time itself is stretching and shrinking based on how fast you're moving relative to someone else. So, to put it simply, the faster you move, the slower time appears to pass for you compared to someone who is stationary. This isn't because your watch is broken or your perception of time is off. No, it's because time itself is actually passing at a different rate. Let's take another example. If you were to travel at 99.99% the speed of light for about 7 years, you'd come back to find that more than a century has passed on Earth. You would have aged only 7 years, but your friends back on Earth would have aged 100. This might sound like science fiction, but it's actually a fundamental aspect of our universe. Time dilation is not just a theoretical concept, it has real-world implications that we will delve into in the next scene. So buckle up, because this ride through time is just getting started. Mathematics is the language of the universe, and it also provides the framework for understanding time dilation. Speaking of mathematics, a significant element in this equation is the Lorentz factor, represented by the Greek letter gamma. This factor is crucial in understanding how time dilation works. You see, the Lorentz factor is a function of velocity, or speed, and it quantifies the amount of dilation that occurs as an object moves closer to the speed of light. To calculate the Lorentz factor, we use the equation gamma equals 1 divided by the square root of 1 minus v squared over c squared, where v is the velocity of the moving object and c is the speed of light. As the velocity v approaches the speed of light c, the denominator of the equation gets closer to zero, making the Lorentz factor gamma increase significantly. Now, how does the Lorentz factor relate to time dilation? Well, the time experienced by a moving observer, known as dilated time, is equal to the stationary observer's time multiplied by the Lorentz factor. The faster the velocity, the larger the Lorentz factor, and the greater the time dilation. Let's consider a scenario where a spaceship is traveling at 90% the speed of light. By using the Lorentz factor in our equation, we find that for every 1 second that passes on the spaceship, approximately 2.3 seconds pass for a stationary observer. This means that time is effectively running slower for the person on the spaceship compared to the stationary observer. It's important to note that these effects become noticeable only at speeds close to the speed of light. At everyday speeds, the Lorentz factor is almost exactly 1, meaning time dilation effects are negligible. So this mathematical relationship, encapsulated by the Lorentz factor, allows us to predict and understand how time dilation occurs. It's a fascinating glimpse into the fundamental nature of our universe and how time itself is interwoven with the fabric of space. With the Lorentz factor, we can accurately calculate how time will dilate under different speeds. Time dilation isn't just a theoretical concept, it has real-world implications that we can observe and measure. One of the most common examples of time dilation in practice is the Global Positioning System, or GPS. GPS works by using a network of satellites that orbit the Earth, each one sending out signals that our devices pick up. These signals contain precise time-stamped information, which our devices use to measure the distance to each satellite. By triangulating this data from multiple satellites, our devices can pinpoint our exact location. But here's where Einstein steps in. These satellites are moving at speeds of about 14,000 kilometers per hour, and they're also 20,000 kilometers above the Earth. According to Einstein's theory of relativity, both of these factors, the high speed and the weaker gravity, cause time to tick slower for the satellites than for us on Earth. If we didn't account for this time dilation, GPS would be off by about 11 kilometers per day. That's the length of a marathon. It's only by applying Einstein's theory of relativity and adjusting the clocks on the satellites that the system can provide the pinpoint accuracy we've come to rely on. So while time dilation might seem like a concept confined to the realm of theoretical physics and science fiction, it's actually at work every day in the technology we use. The same principle applies to other high-speed or high-altitude technologies such as space travel or even high-precision atomic clocks. It's a testament to the power of science that we can take these mind-bending concepts, like time running at different rates, and use them to our advantage in practical applications. The understanding and application of time dilation are vital in our modern world, helping us navigate both literally with GPS and figuratively through our understanding of how the universe works. So, the next time you use your GPS, remember that it's only accurate because of Einstein's theory of relativity. Time dilation is one of the most fascinating concepts in physics. And so we've journeyed from understanding the basics of relativity to unraveling the enigma of time dilation. We've seen how relative motion and the constancy of the speed of light intertwine to produce this mind-bending phenomenon. We've delved into the mathematical backbone of time dilation, the Lorentz factor, and how it quantifies the way time stretches as we approach light speed. We've explored practical scenarios, from the twin paradox to the crucial role time dilation plays in our GPS systems. Remember, time dilation isn't just an abstract concept. It's a fundamental aspect of our universe, subtly shaping our perception of time. So keep exploring, keep questioning, and keep unearthing the marvels of relativity. So the next time you're running late, just remember, it's all relative. Thanks for watching, and keep questioning the universe around you.